Okay, so this one, I'm going to share the screen. All right, so we're sharing now. That one's converting. I'll post that just kind of as an administrative one. And then this one will be more getting into the topics. All right, so the next set of topics, and usually this can take a while, so I'm not really, I don't plan to rush these ML word problems. I actually think these are very important. We're not going to do any coding, but instead the idea is you have a problem, any problem. Like you decide that you want to build an AI startup, right, related to dealing with trash or something like that. So you start from that, and then how would you start building the model and the data, and how do you think about all those things, right? And then there's the terminology, of course. So we're going to have terminology that we need to all kind of be um, clear on, so that whenever we're talking and discussing these things, we're correctly naming things. So we're going to have, like, what are samples, right? So we want to define what a sample is. I keep saying features, right? So what exactly is that, right? And things like that. What's a tensor? I keep talking about that. And what are the dimensions of a tensor and so on. Okay. So that's sort of the idea. So terminology and then word problems. How do we start thinking about machine learning? Okay. So that's the what I'm going to do next. So I usually don't do slides, we just code, but for the first day, I do have these slides just on some terminology that we want to have, which is these PowerPoints. And then what I have here is these word problems. I call it in-class problems, MO pipeline. This might be your first homework assignment, which I usually do. It's just I give you 3 to 5 problems, and basically I ask you to answer certain questions about them as they relate to machine learning. Okay, so you'll see what I mean. And then there's this ML pipeline here. So let's start just with some of the terminology. So I'm going to move this over here. And this is a PowerPoint. So, all right, so here we are. Okay, so just a few slides with some of the terms. Yeah, great. All right, so you should be seeing these. All right, so machine learning kind of introduction. Um, so let me. All right, so some of the terms, right? So the terms are machine learning. There's this term features. There's this term big data. There's this term deep learning, right? So these are the ideas. We've got also the tools that we will be using. So machine learning, what's the definition of it? Essentially, there's AI, right? So you guys know that there's actually artificial intelligence. Machine learning is actually a subset of AI, right? So AI can be other things, right? Not just machine learning, because AI can be heuristics, right? So rules. Actually, large language models, for many years, up until 2017, I guess, or before, probably a little before, they were just kind of like rules. People were trying to understand the structure of language by creating all these rules. Think about it. You were trying to understand the syntax, and just the problem of grammar, which today it's easy for large language models, right? It's amazing how LLMs have perfect grammar essentially. But that problem in the past was really difficult. And people were trying to approach it based on these ideas of people like Marvin Minsky, et cetera, and creating these knowledge bases of rules, just rules for this and rules for that and rules for this. And that didn't work, obviously, right? Because we didn't get LLMs as we got them today. Instead, we got them. LLMs are not rule based. LLMs are deep neural networks that learn from data. Do you guys understand the distinction? So, yeah. So machine learning essentially then means that you have a model and you let the model learn from the data. instead of you going in and putting in a whole bunch of rules and things like that. Okay. So yeah, so that's machine learning. Features are the way that you describe something. And this is why we do the work problems starting today, is because really the best way to understand what a feature is by doing examples. So what is a feature? But people describe them as descriptors, actually. So characteristics of something. The thing that you're looking at in your machine learning problem, which sometimes you will call that a sample, right? So that's the terminology. So features are like, okay, how do you describe, you know, this remote control, right? So all remote controls. Well, it depends on your problem. Maybe you're going to describe it as the length of it or how heavy it is or something like that, depending on your problem, right? So obviously I could describe this. I could give like 1,000 different descriptions, right, for this. So you select the ones that are going to be more useful to solve your machine learning problem. That's essentially the idea. Big data, I almost feel like this term is kind of old already, right? But big data just meant that we went from small data sets to massively large data sets, right? And so that's what that means. Obviously, a lot of what happens today is based on really massive amounts of data, right? The state of AI, machine learning, deep learning, is using really large data sets. That's why we need GPUs. And in this course, we need one GPU. You may or may not know this, that companies like Meta, et cetera, use thousands of GPUs, hundreds of thousands of GPUs, right? So much, just building those clusters is a very challenging problem. It's very difficult, right? Not everyone in AI knows how to do that, actually. Don't think that. Very few people actually know how to do that. So then we have deep learning. Deep learning, just like machine learning, is a subset of AI. Just like machine learning is a subset of AI, deep learning would be a subset of machine learning, right? So it's a class of machine learning algorithms, those based on neural networks, essentially, right? So there are algorithms in machine learning that are not based on neural networks. KNN is one of them. Decision trees, random forests, they're very interesting, sometimes very powerful machine learning models, but they're not based on neural networks. And then those that are based on neural networks, have a specific structure. And when they get very deep, then they're named, they're called deep learning algorithms. So we need to discuss quite a bit to get to that definition, but for now, they're just neural networks that have many layers, let's say. Okay. Stop me at any time, guys, if you have any questions or anything you want to ask or talk about. Okay. Tools that we will use in the course. This one's kind of important. So I usually actually like to show you a tool called Weka. I think it's a really nice way of understanding a lot really quickly. Right. So this is a tool that you can still use. I use this tool all the time. So I use it for like prototyping. Like I want to visualize a problem really quickly. I go to Weka, actually. I don't want to spend days or hours building something really complex, right? So this is a tool that I like using. Even if my data set is very large, I just randomly select a subsample of it, load it on Weka, try a few things, and it really helps me to understand what's going on. So I'll show you this tool. This tool has been around for many years, like easily 25 years. It has been improved to include many things. But yeah, this is one of the tools that you can learn this in like an hour, and I think it's very helpful. Python, obviously. So we'll be using Python. NumPy, we'll be using NumPy a lot, right? So numerical Python. For those of you that, if you ever use like MATLAB or something like that, NumPy is kind of the version of that for Python. And, we'll do a lot of problems and exercises with NumPy. Pandas is another library that we'll be using. This is a nice library for processing the data. All right, so usually I'll read the data from a CSV or somewhere like that. With Pandas, load it as a Pandas data frame. I can do lots of things with that Pandas data frame. Now, the focus of this course is not Pandas, but we do have a course, the visualization course, which covers how to use these tools in more depth. So that's what Professor Gridgen, I think. All right, but yeah, Pandas is another tool that is just essential, is how it works. Essentially, the way that works is like you go from data to Pandas to NumPy to PyTorch, kind of like that, right? And that will be the overall approach. sklearn is another tool. We'll use it for, illustrate some of the traditional methods. I use it just a lot of people. I think, a lot of people just still use sklearn for metrics, for processing data. Is just something that a lot of us of a generation started with sklearn. It works. Why change code that works, right? One funny thing about all these libraries like NumPy, PyTorch, TensorFlow, sklearn is they all kind of like copy each other. So they're all trying to be like the other one. So eventually you can do the same thing in almost any one of these frameworks, right? And you switch back and forth, and there's nothing wrong with that. Okay, there's nothing wrong with that. It's whatever is you're more comfortable with. But yeah, in my overall pipeline, I'll use these libraries. There's TensorFlow and PyTorch. I personally do not like to use TensorFlow. I started with TensorFlow when TensorFlow 1 came out, but when they switched over to TensorFlow 2, which was an upgrade, I think 2 years ago maybe, they made such a drastic change from TensorFlow 1 to TensorFlow 2 that basically, the learning curve was so high that you could just start with PyTorch and it was kind of the same. And I just switched over to PyTorch because I do believe, and many people believe, that PyTorch is easier actually to grasp. Nowadays, I think TensorFlow dominated for a long time, but I would argue that PyTorch is now dominant. We won't do anything in Keras in this course. So I don't like Keras either because it's like too simplistic. That's what I don't like about Keras. So TensorFlow, super hard, right? At the low level. Keras, too easy. It's trying to abstract too much. So think of PyTorch as somewhere in between. You know what I mean? Like you can do more things with it, but at the same time, it's also somewhat easy. I think that's a good analogy on how to view PyTorch. Not exactly, but I would say that. Like definitely TensorFlow 2. I'm sure they've improved it. The problem with Google is that they have like 17 ways of doing something and nothing is compatible with the other thing. It just gets really frustrating. And PyTorch actually addresses that really well. Like things are, they really do a good job, at least so far. But yeah, I would say that. So in the TensorFlow ecosystem, if you want to do a lot with TensorFlow, it gets a little bit difficult. Or you get Keras, which is too much of an abstraction. So whereas PyTorch is like somewhere in the middle, the best of both worlds. We'll code a GPT with PyTorch, no problem. Or stable diffusion, right? Just like we can code a simple multi-layer perceptron, right? And it's consistent, right? So that's one nice thing about this is so we'll take this approach all the way from regression with PyTorch all the way to really complex algorithms. And the nice thing about it is everything builds upon things that you have learned before. So it's really a consistent pipeline. Okay? But yeah, so yeah, the course is PyTorch. For parallel things, there's like been two approaches, Hadoop or GPUs. I don't cover Hadoop in this course or Spark. Instead, for parallel, you'll be using, as I said, Colab is what I recommend, is probably the best thing. And another reason why I think it's good that you should learn Colab. If you ever go, if you're doing AI, right, and you're going to do some kind of an interview where they give you a machine learning problem, right? And, you know how they do like coding exams or something like that? Guess what they're going to ask you to use? Colab. You know what I mean? So that you can expect that. They'll expect you to know how to use it. So they'll say, you'll do this in Colab and here's the problem. So it makes sense to know to use Colab, and it's very powerful and just keeps getting more and more powerful anyway. At least for the purposes of this course, Colab should be sufficient. And like I said, if you're ever training something that requires more time, you save the checkpoint and continue later. So we'll talk about that. Yeah, but yeah, there's GPUs, there's TPUs, special kinds of parallel processors, but essentially GPUs is what we'll be using. All right. Any questions so far? Questions? All right. So what is machine learning? So we've talked about that, methods for predicting, detecting, grouping data samples based, using a model. But yeah, it's learning from data, right? That's essentially what it is. And, it used to be that you're just training to classify things. Today, that idea has been expanded. Obviously, you guys know about generative AI and all those things. So there's a lot that you can do. There's a lot of ways that you can use that data to create something intelligent. But we train the model from the data. So we'll talk about that. Why machine learning? There's too much data. Yeah, so this is kind of a motivation that I've used in the past about machine learning. So have you guys heard about Kepler? Do you know who Kepler is? Like a physics or astronomy person? Hmm? Is it what? Laws, Kepler laws? Yeah, so Kepler is related to like understanding the gravitation or the rotation of like planets around stars, for instance, right? So it was the whole progression of all these different astronomers, and Kepler inherited or collected all this data. And based on all that data, manually, he was able to figure out the laws of the gravitation of bodies around stars, right? But essentially, what he did was what machine learning does. So, he won, he's famous, right? So think of, this kind of should put like, give you a perspective. Kepler is somebody that's in books, right? Um, because he many years ago collected all this data, did all this research, astronomical research, and then he was able to figure out that, the moon goes around, the Earth, or the Earth goes around the sun, and it follows these elliptical gravitational trajectories, etc. But he figured all that out just because he was intelligent, right? And he was able to like write out the math equations or whatever. But that's what machine learning does today. So, and machine learning is not getting any Nobel prizes or anything like that. But essentially, he took some data, analyzed it, and came up with a model. And machine learning does the same, right? So you collect some data and then you build a model about the world. So building models by hand is labor intensive, right? And machine learning models can do this with more data and much faster. Yeah, so lots of data today. So as a statistic, I don't know if you know this, but something like GPT-4, etc., was trained on pretty much all the text of the internet, right? So it takes thousands of GPUs, 3 months, and it's basically all the text, all the books that you can make available, etc. So it's a lot of data. So we need to have a lot of computing power. All right, so some additional concepts. So here I'm going to talk about two ways of dividing machine learning, which are the old ways, I would say, supervised learning and unsupervised learning. So this is like a classical starting point. So what's the difference between supervised learning and unsupervised learning? What do you think? Good. Yeah, good. Label data, yeah. Mhm. Unlabeled data, right? Yeah, exactly. So you have all these images, and then you put a label. These are cats. and then you have all these other images, and you put another label, this is a dog or something. And so the machine learning model then learns from that, learns to correlate the information in the images to the label. And that is called supervised learning. Okay. And then unsupervised learning, as someone said, is you don't have the labels essentially. Okay. But nowadays there's other variations of that, like semi-supervised or things like that. But yeah. Yeah, reinforcement learning. So there's a lot more, right? So definitely the all these concepts of AI have expanded. But essentially, you can think of this as a range from supervised to unsupervised, and now there's things in between that are very interesting. Okay. So yeah, usually when we start machine learning, we start with supervised, right? So a lot of the things will just have labeled data, and we will start learning about it. Unsupervised data, so one thing that I will say, and this is where like something like Weka is really nice, is that we will see that for supervised learning, we have a set of algorithms. And for unsupervised learning, we'll have another set of algorithms. So some of the supervised learning algorithms will not work with unsupervised data. Do you see that? So we will have to know the difference. So traditional things like KNN, neural networks, like multi-layer perceptron in particular, will work for supervised learning. And then other algorithms like clustering, for instance, k-means clustering will be specific for unsupervised data. Okay, we'll see that. And then there's going to be some tricks that we will learn about where the data was not labeled by a human, but it just existed in a way that there were correlations, so you can use that. So text is a perfect example of that, right? So large language models learned not by looking at text and then the annotation of that text by a human. Instead, large language models just learn by what? You give it the actual sentence and the fact that we have structure in language, right? So the cat is sleeping. That just existed there. So the analogy is that cat and sleeping, cat is like the sample and sleeping is like the label. Do you see that? But no human went in there to create that. I mean, humans went in there initially when they wrote the book, right? But that's essentially how it works. So that's why those things are somewhere in between, right? It is sort of supervised, but at the same time, no human had to create it, which would have been really hard to do. All right, so people get, they at some point figured out that would work, essentially. Does that make sense, guys? That example of how language has structure, therefore you can learn correlations between words. All right, that's obviously a topic we'll explore later on, right? So today I'm just giving you some ideas. But yeah, supervised and unsupervised is one of the ways of dividing machine learning, and then we'll just add more ideas to that. I've mentioned this. Okay, we have 20 minutes till the break, so can keep going. What else do we have? We have features, data sets, data pre-processing, and performance metrics. So there's some traditional performance metrics and there's some advanced performance metrics. So nowadays, you guys, so for instance, there's the classical like F1 measure or precision and recall. Those are traditional performance metrics. But nowadays, when you're building something like a Chat GPT, you don't measure Chat GPT on F1, right? You use something else. So nowadays, something like Chat GPT is trying to solve math problems, right? High school math level problems. So then you create metrics just for that specific task, right? So there's way more metrics nowadays, okay? So there's metrics, when the first transformer came out, way before Chat GPT and all that, it was basically just to translate from one language to another, right? And then the metric was something called the blue score, for instance. These are just various metrics that have been created over time. So we'll look at some of those, and we'll start obviously with the basic performance metrics related to supervised learning. Data pre-processing and data sets, as I said, if you're working in data science, that's like 80% of your work is just taking that raw data and converting it into a specific format that we will use for machine learning. The way that I think about it is got raw data and I want to convert it first to the vector space model. All right, the vector space model is this concept that's very beautiful, right? It's an amazing, interesting concept. But it also is very helpful because once you put your data in that format, you can then use any machine learning algorithm. Okay. But that conversion is not always trivial, right? That's where that data wrangling idea comes in. It can be pretty hard. So data sets are important, being familiar with data sets, doing the pre-processing of the data. It's pretty important. I have that machine learning pipeline figure that we will discuss in a second. And we'll take a look at that. All right, so these are some of the traditional machine learning algorithms. So naive Bayes, decision trees, random forest, KNN, linear regression, nonlinear regression, logistic regression, neural networks, support vector machines. Okay, so all of these are here. If I just think of neural networks as going as up to the multi-layer perceptron, then these would be like traditional or classical machine learning algorithms. We will do at least one one lab or one assignment where we look at all of these, at least from the point of view of using them, right? I may not discuss the algorithms because, there's a lot of algorithms involved here. But we will definitely cover linear regression, logistic regression, neural networks, and to look at the algorithm. Maybe decision trees is one algorithm I'll cover, given that that's a tool that's actually really powerful. Today, for tabular data, which tabular data is the kind of data where it's not images, it's not text, but instead it's just like, imagine you have this room with a lot of sensors, right? Imagine temperature and pressure and something like that. So you're collecting all that data every hour, right? And then you're associating something like how many students were in there or something, right? So all that data that you're collecting is just essentially like an Excel spreadsheet. Imagine every row is like a sample, every column is a measurement that you took over time, and then you can train a model with that. So that's usually called tabular data. So for that kind of data, you don't need to use neural networks. In a lot of competitions, currently, the decision trees actually do better. All right, so you can use neural networks, obviously, but my point is with this is that, even though neural networks and deep learning is really popular, the other traditional methods can also be very useful, right? And there are some applications where they're actually preferred, right? Such as when you're dealing with tabular data, you may want to use decision trees, random forest, or something called XGBoost, which is one of the tools that I'll show you for that particular problem. All right. Any questions about that? No questions? All right. But yeah, so these are some of the traditional machine learning algorithms. So what is deep learning? Essentially, deep learning is a neural network where you have layers, right? So we're going to spend a lot of time talking about this. We'll definitely code this. And I'll try to give you some of the background on this, which I think tensor operations actually will be critical to understanding that, because your very first set of examples will be to understand the underlying operation of neural networks. Anyone know what the underlying math operation of neural networks is? There's one operation that is like the most important. Update the weights, yeah, but there's a math operation to do that. That is the underlying operation for neural networks. It's not the activation function. It's the matrix multiplication. Okay, so it's a multiplication. Okay, so we're going to learn that these are values. These black little balls are values, and these links are also values. Okay, so to produce these, the next layer of values, what do you think we do? We need to multiply the little balls with the little links. but there's a lot of them, right? So we need to do that efficiently. We can't do that one by one, like in sequence. If you did that, you'd never finish. Okay? So how do you do that? You do that with a multiplication, but not a per variable multiplication, instead a matrix multiplication. Do you see that, guys? So that's a key operation. And the 100 plus problems that I'll give you should help you to understand that better. Okay? Right? So we'll get to that. But yeah, so this is a neural network, but it's a deep neural network. And essentially because you're performing those math operations several times, right? So you have these that you could consider the starting point, the inputs, times some weights, perform that, and oops, sorry. Yeah, and you get this layer. Then what do? You find out another set of links, and you multiply those links times this new set of values in this layer. How do you do that? Matrix multiplication. And what does that give you? The values in the next one. Do you see that? And then you just keep doing that over and over and over. Okay, so there's that operation to build that architecture going forward. And then there's going to be the process of coming back, the back propagation, which is updating these values, the weights, right? So these are two things that are happening, but mechanically, you're just building this pipeline of operations essentially going forward. All right, so that's what a neural network is. And then neural networks with more layers between the input and the output layers are essentially, the term is to call them deep learning. Matrix multiplication operations are what makes this work really well. And of course, GPUs do that very easily. So that's actually the advantage. So think of it this way. To do deep learning, you need matrix multiplications. And not someone, NVIDIA, right? The trillion-dollar company created processors, actual physical processing units that are really good at doing matrix multiplication. Okay? So that's pretty important. Okay? But yeah, so that's the idea with deep learning, and we'll definitely discuss this quite a bit. And ask questions if you have them, please. Okay. See what else we have here. Right, so I do have a nice figure for this one. But the machine learning pipeline is, as I call it, is just going from the data all the way to a trained model and performance metrics. So that's usually the complete idea. All right, so we'll have something like the data in some format. We pre-process the data, which means cleaning it, normalizing it, putting it in the format. Which format? The format of the vector space model. It's like an extremely elegant idea. Okay, like once you start to grasp it, it's really nice. And then once something is in that vector space model, essentially it's like it's formatted correctly, and then you can feed it into any of your machine learning algorithms, usually, right? At least for the tasks of supervised or unsupervised learning. And then, of course, once you have a model, you're going to evaluate it with some kind of performance metric so that you can compare it to other models. And that's the idea. Okay, data set formats. So there's a lot of formats for data. libsvm, ARF, and many more, JSON structures, etc. Usually what we're going to be using a lot is the CSV format, right? So you guys know what that is, comma separated format. The idea is like Excel. That's where Excel is kind of nice as an example, right? Rows and columns, right? So what's important is every column represents a feature. And then all of your samples, right? So have to be consistent in using that column to represent that information, right? So let's say that you decide that column 3 has something to do with age, right? And then you have 100 rows, which represent 100 people, so 100 samples. Then all people have to use column, what did I say, 7 to represent age. If you use column 6 for some of them and column 7, it's like garbage in, garbage out, right? So you made a mistake. Okay. Yeah, so that's important. We'll see that CSV files are essentially what we will be using to start with our, we'll start with Iris probably or something like that, the Iris data set. But yeah. But yeah, it's like Excel rows and columns. Rows are the samples, features are the columns. Okay. So what is a sample? This is a critical one that kind of leads us into this will lead us into the word problems. So in the word problems, you'll have like a problem, and then you have to identify what are the features, what is the sample, and you'll see that samples sometimes can be very obvious and easy, and sometimes not so much. So if you're dealing with images of cats and dogs, basically every image is a sample, right? There, that's the thing. Sample 3, picture of a cat, right? But sometimes if you're looking at a network attack, and you're trying to build a model for that, what's the sample? See what I'm saying? So not, especially if you don't know about network security, right? Well, what is it? What's that? Update a packet. Yes, that's true, but that's good. A packet, you guys know, right? So a little bit of information in a specific structure that carries the information for the internet to work. But what if I have a problem where one packet is not enough? Like let's say a denial of service attack, right? Where you get thousands of packets. So what's the sample then? That's a feature of the packet. You see what I'm saying? So you have to really think about that because you have to be consistent. You can't be using packets for one sample and not something else for another sample. You have to be consistent there. Okay? So maybe you build 2 models. One model of just packets and a second model of something else. Right? So samples are important. And that's one of the things that I'll discuss is whenever you're dealing with a machine learning problem, you want to answer, okay, what's my sample? And why. All right, so we'll see that. All right, so defining your sample is critical. Yeah, in text, what's my sample, like a sentence or a paragraph. Images, obviously, that's a very easy one, and other things. Data sets, there's a lot of many data sets. You guys know there's Kaggle, for instance. So whenever you're looking for data sets, you can go to Kaggle. The UCI database is another one. So there's lots of different kinds of problems. There's we'll do some cybersecurity. I have some nice cybersecurity data sets. So maybe one of the homework assignments will use those. But there's different kinds. The iris data set is pretty famous, is about the iris flowers. So that I really like to start with that one because it helps to illustrate what's a sample, what's rows, columns, features, all that. So we'll definitely start with something easy like that. Phishing data sets, right? So those are going to be more like text-based, possibly, or metadata-based. Networking things, as I mentioned, and various other things. How do you, ransomware, right? How do you start to think about that in the context of machine learning? Company is using machine learning. This is funny. I was looking at this slide today and I was going to change it. And then I'm like, no, you know what? I'm not going to change it because it just shows how fast this moves. So obviously there's a really big one missing here, right? What's one company using machine learning today that's missing? NVIDIA. What's another one? OpenAI, right? ChatGPT, right? So, and then there's other ones like there's this Claude tool, Perplexity AI. Oh, right. And I did this like a couple of years ago. And I only had Tesla, Facebook, Google, Amazon, which they're not doing well in AI. Apple, not doing well in AI. And, not including those, but it's funny just how quickly it moves. Right? So there's a lot of companies, for sure. So this is interesting. Okay. Cybersecurity, one example of like a specific domain. So cybersecurity, right? So I picked this one, but there's healthcare or other sectors. So a lot of these companies are using machine learning. There's specific companies like Blue Vector, which I think they were purchased by Comcast recently, but they were doing like intrusion detection systems that were machine learning based. Northrop Grumman, they're automating a lot of things, right? There's a new, again, there's another company that's missing, Anduril. If you've ever, Anvil or Anduril, they're also doing that kind of work. So definitely a lot of companies in this space. Okay. Okay, so yeah, so this is almost the end of these slides. Just a few links here. Sample code, I already gave you that, right? So you know there's two links where I'll usually post all the code for this course. The environment, just to repeat, PyTorch, I don't recommend you use virtual machines at all. Just use Anaconda on your Windows, Mac, or Linux. It works really well. And start playing with Colab. I do recommend Colab. It's pretty nice. It's one really good Google product. Usually in the course, I get students that have their own GPU at home, usually like gamers or things like that. Um, yeah, so obviously what you get when you have your own GPU is you're not restricted to that 2 hour limit, for instance, where you have to save checkpoints. You can train for 2 days without a problem. Nowadays, GPUs are expensive. Um, I think 2000, right? The 4090 is like the current GPU from NVIDIA, um, which is like 3 to 4,000. That's affordable to some of you. The more powerful GPUs, I think like eight, hmm? A100s cost $30,000, right? So they're very expensive. But if you want, I mean, if you want to know how to build your own physical GPU box, it's easy. You just need a powerful GPU, a lot of RAM memory, essentially. But it costs like $4,000 to $5,000 to build one of those, right? So I don't recommend it unless you were just doing that, a lot. Like if you're consulting or something, very expensive. All right, yeah. So that's the summary. So that's the end of the slides. Okay. So it's 6:19, so this is a really good stopping point. Okay. So we covered the slides, just some terminology to kind of get you to start thinking about these things. We're going to take a 10-minute break from 6:20 to 6:30, and then when we come back, we'll start with word problems. Okay. So the idea and so the next module, the machine learning pipeline, and you'll see what I mean by word problems and so on. Any questions? All right, so we'll stop here and we'll take a 10-minute break.